All right, I don't know where everybody is, but we're going to start because I have to leave early today. Okay, so we're going to interrupt the lecture around before 1:30. By the way, no lecture tomorrow, I'm just too tired this week. Okay, and spring break is coming, so you're tired of me as well. Okay, let me just put the microphone because I have no energy to speak. There's a bunch of topics that some are application-oriented, some are fundamental that we need to cover. So what I'm going to do is I'm going to start with some issues that they are very fundamental. And assuming we will have time this semester, we will come back to these topics later on. So I need to give you a very general perspective of variational inference and in the context of expectation maximization. All right, so let me remind you, is there you hear any noise, or it's me only?
It's okay.
Okay. So let me remind you the fundamental problem that we motivated with mixture of Gaussian distributions. So we basically we postulated the problem with, and the battery has died. When do you need them? Suvik, do you have anything? Okay, I can see this is partially alive, all right? So we had this observable variables x, right, and these hidden variables z, and we wrote basically the likelihood as this integral, which is intractable in the space of z, okay? And obviously we explained that doing an algebra on problems where you know the hidden variables is way easier because usually this distribution is a simple distribution. For example, a Gaussian or in general a distribution from the exponential family. So what I want to do today is I want to basically take the algebra to an extra step. There will be nothing new in the context of EM, all right? Literally there will be nothing new, but the methodology may inspire you that there is something to come up later on in this course, and later on as you learn more about machine learning, that is way more powerful and generalizes in many ways the expectation maximization algorithm. So what I'm going to do is I'm going to take an arbitrary distribution on the latent variables, and I emphasize here, this is anything, all right? Any arbitrary distribution, and for this any arbitrary distribution, you can actually write the log likelihood of x as being this quantity with the calligraphic L that you see here, plus the Kullback-Leibler distance between the distributions Q and P. We will prove this on the slide to come. The proof is not very complicated. Just a few reminders. This is just a definition. And obviously here you recognize the joint likelihood of x and z. I emphasize Q of z is arbitrary, and the KL distance, a reminder, minus Q and Q go like that, right? And here is the actual posterior of, P is the actual posterior of Z. Okay, and also as a reminder, the only way that this distance will be zero is if the arbitrary distribution Q becomes equal to the distribution P. So it's, in some sense, can you extrapolate, before I do anything, what the objective of having this arbitrary distribution Q will be, assuming, as you can see here, it says, this KL distance, is zero when Q is equal to P. Thank you. So can you extrapolate what the significance of Q is going to be considering that this KL distance, in other words, what meaning are we going to assign to Q, you think, eventually, even though it's arbitrary? Say it again?
Proposal density.
I don't know what proposal density is. You know, we're not doing anything but sampling here.
I mean, the approximation.
That's a different thing. So an approximation of what?
The posterior.
Of the posterior. All right, so now that's better. All right, so Q eventually maybe sort of meaning we will assign, it will be something that even though it's arbitrary, we will make it to eventually approximate to the true posterior of the distribution Z given X, okay? Obviously this is very fundamental to these variational methods that I will not discuss in depth, but basically the quantity that the equation that we need to prove before we do anything else is this equation here, and give some physical meaning to this functional that you see here, L of Q and theta. So let me prove. I'm going to use the definition of that we said here, this equal to this plus this. So let me start with that, all right, to make the algebra easier. So this is the integral of Q of Z, log of this. So I am splitting numerator and denominator, nothing fancy, and I'm writing this joint distribution as the distribution of Z given X and the distribution of X. All of this times Q of Z minus Q of Z log of Q of Z. So this doesn't depend on Z, so I can put it out of the integral. Integral of Q of Z dZ is equal to 1, assuming that Q is normalized. And then I have this nice term and this nice term. I can put them together, right? Q of log of the joint, you know, Q of log of this is the posterior divided by Q of Z here, plus log of P of X and theta. And this by definition is minus the KL distance between Q and P. So basically we're done, right? So before the equation said this, the likelihood, the log likelihood of X is equal to the KL distance plus this functional of Q and theta that we define it like that, okay? So we have proved this very nice equation, all right? And this equation is very nice because we know that the KL distance is always greater or equal to 0, which means that the likelihood, the log likelihood, is always greater or equal than this functional of Q and theta, all right? And looking at this equation, we call this functional the lower bound of the log likelihood. Will you agree with me? Right? So what is the idea now of the algorithm, basically, that we're going to sort of introduce that eventually is going to look like the EM algorithm? Rather than computing the parameters theta that maximize the likelihood, that's our MLE problem, trying to maximize what? The lower bound with respect now, not just to the parameters theta that we had before when we worked on on the EM algorithm, but also with respect to the distribution key. Obviously, before in the EM algorithm, right, we had, in the M step, we had to optimize the parameters, but also remember on the E step, we had to compute the posterior. So there's nothing different here because Q eventually is going to be an approximation to our posterior because the maximum value of the lower bound happens when Q is actual to the true posterior distribution, right? So everything hopefully will work very nicely, assuming the optimization problem makes sense. So, all right, so let me just graphically show you this. So this is the likelihood, right? Log likelihood, log of P of X and theta. And we said this is the lower bound and this is the KL distance. So in some sense, we want to reduce this gap to 0 and make the log likelihood equal to this lower bound, okay? So we want to make this lower bound as big as possible, or equivalent if you like. We want to make the distance between Q and P as small as possible. All right, so we're going to do this optimization on Q and theta in an iterative process that basically it's a copy carbon, if you like, of the EM algorithm. So let's do the first the E step, all right? So you remember in the E step, what we do is we fix the parameters. So I want you to look on this plot, all right? If I fix the parameters, what happens to this log? What can you tell me about this log likelihood? If I fix the parameters, what, in the E step, does the log likelihood going to change? Do we have to update it?
No.
No, because it doesn't depend on Q, and it only depends on the parameters theta, and the parameters theta are fixed to their old values, all right? So what we need, so this is constant, right? And we're asking, you remember in the E step, we were computing the sufficient statistics, we were computing basically the posterior of the hidden variables. So in this case, we need to optimize with respect to Q. So what is the Q that brings the lower bound as close as possible to the log likelihood that remains fixed? Is obviously the Q that minimizes the distance from the posterior, but the posterior computed at the old values of the parameters. Right? The posterior computed at the old values of the parameters. So if you select Q to be equal to that, you solve the E step exactly. This gap here will drop to 0, so this blue dotted line will go to the solid blue line on the top, and the lower bound will become exactly the same as the log likelihood that is not being updated on the E step. Clear? Yes? All right. So let's continue on the M step. On the M step, we will, you remember, we basically, what did we do in the M step in the, in the EM algorithm? Remind me. What did we, as soon as we calculated the sufficient statistics, then we started with what? Tell me a complete word. What did we start with? Before we start doing optimization. We calculated the joint data log likelihood, but because we don't know Z, we calculated instead what? The expected data log likelihood. The responsibilities, we calculate them on the E step, right? So we calculate the expected data log likelihood. So here, the equivalent to that step is to actually calculate this lower bound, okay? Using the posterior that we computed at the E step. And obviously you can see this indeed plays the role of responsibilities. All right? And you can actually see, and I will show you this explicitly, this is by definition the lower bound, right? Theta here is, this is the unknown parameters, right? These are theta all. Can we immediately see if you take this p times log of the numerator, you basically get the functional that we optimize on the M step? Can you see that? Right? This is the joint log likelihood, and what is this? This times that is the expected data log joint data log likelihood. Can you see that? And this times that, it's just the entropy, and because you integrate on zeta, it doesn't contain the parameters theta, so it doesn't matter, the denominator. So in principle, this lower bound is very much what we had with that functional Q when we worked on the M part of the EM algorithm. So again, we calculate this lower bound, and we're going to do optimization of this with respect to the parameters theta. So let's see this graphically, right? So don't read anything, you just look at this picture. So this is where these, let's say this is where we finish the E step, all right? And the log likelihood with the all parameters was from here to this red line, dotted line. When I update the parameters, because this is what we're gonna do to the M step, what do we expect to happen to the likelihood? Right? Remember, this is an optimization problem that has only one objective, to optimize the likelihood. So what's going to happen when I calculate the log likelihood, but with the new updated parameters?
Increase.
You better increase, right? Unless, of course, you already reached the maximum. So it will increase and go from this dotted red line, will go up there, okay? Is the KL distance going to be 0 the same way that it was in the E step? And why, yes or why not?
No.
So no why. why the KL distance now is not going to be 0? You remember Q was computed, right? It plays the role of the responsibilities with respect to what parameters? All parameters, and it's fixed. But P is now what P? Using the new parameters, all right? So there's gonna be a gap of KL, all right? So both the lower bound is gonna increase, there's gonna be an opening in the KL, but those two together will give me the new log likelihood, okay? I don't have to go through this slide. Basically, it shows you that this lower bound is basically what we used to maximize. This is the expected joint data log likelihood, right? Plus some constant. So basically, the two things in principle are the same, but hopefully you can appreciate that this variational method with this arbitrary Q to start with is way more general than the way we set this EM algorithm to start with. All right, nothing new, all right, so I keep you read all of these things. So let me try to give you a visual representation of how this optimization process works, looking very, very carefully on this diagram. I mean, obviously, this comes out of Chris Bishop's book, right, and you see a diagram tells you millions of nice things. And that's why practically every book, every paper that uses this type of techniques has cut and pasted this beautiful diagram from Bishop's book, because everything is there, all right? Everything is there. And even though it's a schematic, it tells you more or less everything you need to know about these variational approaches. So let's look at this red line here. This is this log likelihood, and I'm looking at this as a function of the parameters. Right? So really what the original problem was to find the MLE estimate. So we want to find the parameters theta that maximize this log likelihood. You see that? This is where we want to be, okay? So we start with some initial parameters, all right? And in those initial parameters, all right, we calculate this lower bound, all right? And I proclaim that this is how the lower bound looks on the all parameters. And I want you to look here and tell me why this diagram looks like that on the all parameters. I mean, when I look at this calculation of the lower bound, I see two things. First, that it is exactly equal to the log likelihood at this point. And even more importantly, that the slope of the two curves is the same. First, why the two things are the same? What happens on this step? You remember the log likelihood remains what? Constant. All right? The log likelihood remains constant, and the KL distance what happens to the KL distance? 0. All right? So the two things coincide. But why is the slope the same? Remember, what do we do in this step? What is the optimization problem in this step? As a matter of fact, what's the optimization problem in the context of the KL distance between Q and P? If we want to state the E step as an optimization problem in terms of the KL distance, what is that problem? Find Q to do what? To minimize the distance of Q from P. Okay, all right? So which means the derivative of the KL distance with respect to the parameters is equal to what? 0, right? From the optimization problem, so the slope of the two things is the same. So this is why in this step the curve looks like that. So once we have the lower bound, right, then you are solving the M step and you say now, what I'm going to do now is I'm going to optimize this. So if you optimize it, it will bring you basically to this theta nu. And then once at that theta nu, you will start a new step, which means you're going to calculate a new lower bound that's going to look like this. And again, you notice the values coincide with the log likelihood at this point, and the slopes coincide. Then you will maximize that, and it will bring you up there. And then in another step, you found the correct solution to the MLE estimate. Okay, so this is a very nice representation of the EM algorithm. All right, something that you know, I forgot to. So I don't know if this exactly belongs on this variation method, this slide, but something that I forgot to mention that is extremely significant is for the type of models that we discuss is that the posterior of z given x factorizes over the data points. This is extremely important. So what that means is that if you look at the posterior of Zn, it only depends on xn and the parameters theta. So for each data point, right, for each data point, given the parameters, okay, the Zn doesn't depend on anything else, okay? So if I want to take the, you know, this x is all my x's in my data sets, right? So where do I have x1 to x capital N, and z are z1 to z capital N. This distribution here, the algebra is trivial, there's nothing there. This distribution here factorizes over the data points. This has a lot of implications in more advanced methods. So effectively, you know, for each data point xn, there is only one Zn given the parameters theta. Okay, given the parameters theta. All right. So before we finish with this discussion of the variational version of the EM algorithm, which is again sort of an introduction to variational methods that hopefully we will have time this semester to discuss, you may ask the following. Okay, we did the MLE estimate, and I think I also did a map estimate, but can we just see the general equations, how from MLE you actually start computing the map estimate of your distribution given this, the data X. So what I have here is I use Bayes' rule to write the posterior of theta given the data X. These are the visible data, right? We don't know the latent variables. So P of theta given X is the likelihood times the prior defined by the marginal likelihood, all right? I take logs and I write the log of the posterior to be the log of the likelihood, the log of the prior, minus the log of P of X. And we already have seen that the log likelihood is the lower bound plus the KL distance. So I plug in lower bound plus KL distance plus log of P of theta minus log of P of X. And notice this doesn't depend on Q, right? Doesn't depend on theta. So for all practical purposes, you know, you don't really have to bother about this. And also you remember the idea here is the KL is greater or equal to 0. So this log of P is greater or equal to L, the lower bound, plus the log of the prior, minus some constant. So can you tell me, looking at this equation, what modifications are you going to do to the E step of the EM algorithm? And what modifications are you going to do to the M step so you can find the map of the distribution of the parameters? So look at this, and I want to hear first, what are you going to change in the E step? And then what are you going to change in the M step? So in the E step, what are you going to change? You have to remind yourselves, again, because you forget very fast. What is the E step? What do you optimize on the E step? Q, all right? What modifications are you going to do? To compute now the posterior. I mean, obviously, to maximize this, right? That's what we need to get the map. You need to maximize this, all right? And so what term depends on Q? Only the lower bound. So what changes are you going to do to this step? Yes, what changes are you going to do to this step? Come on, guys, spell it out. The what? So what changes are you going to do to L? I want to hear an English word. What changes do we need to do? So if I give you a program that does the A step, what will you do to that program to calculate the A step for this that gives you the posterior eventually? What changes do you do in the A step? None. None. You don't touch it, okay? English. N-O-N-E. Okay? So you do none. And what change do you do in the M step? You realize we are all needing a break. Okay? So what change are you going to do in the M step? So what do we do in the M step, right? We're optimizing the lower bound with respect to the parameters. So what do we need to do, to modify this to calculate now the posterior?
Just include the prior.
You just include the prior. So you just throw plus log of the prior and you're done. So if somebody gives you the algorithm, you only have to say plus log of the prior as a function of the parameters and you're done. That's it. All right? So nothing else. All right. Okay, so we're done with that topic. So let me go to something that sounds a little bit abstract, right? Just to convince you that playing with these mixture models, obviously, it's a difficult optimization problem, okay? Because we said that at the very best we can, when you do MLE, you can only guarantee some local maximum. You cannot really say anything that this is a global maximum. So there must be some reason for all that. So what I have here, all right, so I'll do this briefly. So what you see here is we collect some data, right? So the log likelihood for this data, D, is basically, for each data, we have log of, and I write here the distribution as in terms of the joint distribution where Z has been integrated out, right? So this is our famous problem, log of the sum of Gaussians, let's say, right? That's what we had up to now. So there's nothing new here. So what we're going to assume for this type of problems is that this joint distribution is from the exponential family. So for example, you can think that the joint distribution is, I know I omitted here another term, but it's okay because I only need this exponential. So this is a very common assumption for the joint distribution to be in the exponential family. So remember, right, if you take a Gaussian mixture, you remember we did a calculation. If you take a mixture of Gaussians, is the new distribution in the exponential family. When you have a mixture of distributions, is the mixture of distributions in the exponential family? I know we did a homework, or you did a homework on this, right? Didn't you do some homework that you had a mixture of something and says compute the posterior? All right, so what was the answer to that problem? That you have a mixture of exponential family distributions, the mixture is what? What did you declare in that homework? Did the mixture came to be the same family distributions? No? It was not, so if you have a prior that, there was a conjugate prior, a mixture, what did you get for the, what did you conclude? You forgot the homework?
Mixture of the posterior as well.
It was a mixture of the posteriors for the individual distributions, right? All right. So, which means each of those posteriors were in the exponential family, so it's you get another mixture of distributions from the exponential family. There is a difference here, all right? And so when I look at this distribution here, it's not going to be in the exponential family. And you know why it's not going to be in the exponential family is because I don't really know the z's. That's what makes the difference here. If we knew the z's, you know, everything fits very nicely, but we don't know the z's. All right, so by not knowing the z's, you basically have this intractable term there that messes you up. Okay, so we're going to assume that the joint distribution is in the exponential family like that. So let's see if there's anything general we can say about the convexity of the MLE optimization problem. All right, so the complete data log likelihood, right? This is what we need to form in the EM algorithm. Will be, you remember this is in the exponential family, e to the, go back, e to the theta transpose phi, where phi of x and z are the sufficient statistics. So basically the summation over the data is pulled inside the phi here. You sum the phis to get the sufficient statistics, and z is the normalization factor. So if you look at this complete data log likelihood, as a function of theta, the first term is what? It's linear, right? So this is just a given number, all right? This is a given number, so it's a linear in theta. How about z? Well, it says there, and there is a proof, if you're interested to read in this very nice book, that the normalization term z is a convex function. So this overall function, if this is linear, you have minus a convex function, what do you get out of it? What do you get? This is minus a convex function plus a linear function in theta. So the overall result is what? It's concave and has a unique maximum. All right? Has a unique maximum. So now, but this, remember, is if we knew what z's are. So if we knew what the z's are, right? If we knew what the z's are, then indeed we can say something that the optimization problem has a unique solution, but we don't know what z's are. So in our problem, what we need to do is we need basically to integrate the z's out, all right, and take the log, and then to get the likelihood sum over the data points. Okay, so if you look at this distribution, it's in the exponential family, so you will get summation of the data points of log of the sums of the e to the theta transpose phi. This is what we had before, right? We had log of the sum of Gaussians, and this is what I have up there. Okay? So there is a proof, and very general, it's also given in this book, that this log sum x function, log sum x, is convex. And what did we say about z? What type of function z is? It's convex, so minus is what?
Okay.
So convex minus convex, all right, can be anything you want to. And that's the trouble with this type of problems. There's no guarantee that actually you will find a global optimum. All right, so I thought maybe you want to know that these statements are, basically they point to the difficulty when you work with the mixed models, and even with using distributions from the exponential family for the joint distribution doesn't resolve any of these problems. All right. Okay. Remind me, by the way, that I will need to leave at 1:27. Not only leave, run. Okay. So let's do some examples that around the EM algorithm that are a little bit of interest, and you may see them in practice as well. So let's assume the following problem. I have data that come from some distribution, all right? So it can be a Gaussian, can be anything, and that distribution has some parameters theta that I don't know and I want to estimate. And I'm going to assume, think of the data, right? Let's say they're high-dimensional data. You have a data matrix, and each row it's one data point. But I'm going to assume that some of these data points in my matrix, capital X, are missing, right? So in some rows, if let's say my vector is 100-dimensional, I only know 50 of the elements in that row. The other 50 elements are missing. So what I'm going to do is I'm going to define a matrix Oij. I will be the row in the data matrix, and J will be the column. So when this is equal 1, the J component in the data case I has been observed. I know it. If it is 0, means I don't have it. So the question is, if somebody throws, let's say, data that are incomplete, can you actually do an MLE estimate if you know the type of distribution, even though half of your data have not been observed? Can you actually use the EM algorithm to account for what is not known? Do you see what the picture is? This is the same thing, right? Somebody gives you an image, literally the same thing. I give you an image, and many of the pixels in the image are missing. And effectively, I say, you know what? Let's put some Gaussian random field representing the image, and you will have to fill the gaps in the missing pixels. Here I'm doing it in terms of distributions, and let's say I'm going to assume in this case, let's say that all the data come from a multivariate Gaussian. So the idea is here, yes, we can literally do an MLE estimate for the parameters by filling the gaps by somehow extrapolating and using ideas from the EM algorithm. So here's the problem. We assume what distribution we have, right? So you need to do that. So once we assume the distribution and we know what parameters we're looking, we're saying, find the parameters that maximize the likelihood, but you notice the likelihood involves only the visible data, the ones that we have observed. And also here, we know this matrix omega that says what has not been observed, okay? So we want, in everything we have done up to now, right, says find the parameters to maximize the log likelihood, but here, the likelihood, this involves only part of the data because there's a lot of unobserved things. So what I'm going to do is, how do we use the EM algorithm? The idea is very simple. Think of a row in the data matrix, and this is, let's say, the row I, and I'm going to write the distribution of xiv, so the vector of all the visible variables in that row, to be basically an integral that averages over the hidden variables. Right, you say, I don't know the rest of the values, so I'm going to integrate them out. These are the values I wish I knew, but I don't know what xh is, right? So I'm going to integrate them out. So basically, the likelihood that we want to maximize with respect to the parameters, it's really nothing else but a summation over the data points, right? So you think of your data matrix X of all the rows, and then of the log, and you write basically the likelihood for each data point to be a summation where you are integrating out the hidden variables in that row. Nothing fancy, right? I mean, you can do this, basically the same algorithm to fill the gaps in an image. All right, so basically we have a direct application of what we have seen in the EM algorithm, right? So we have a hidden variables that are defined by this matrix O, so we know where they are, and we want to basically maximize this log likelihood. So what we're going to do is we're going to use the EM algorithm. This is a fantastic application to see the EM algorithm in practice. So first you need to, before you go to this step, right, you need to start with some MLE estimate of the parameters. So usually, whatever values, for example, if I look at one row and 50% of the elements are missing, maybe, I fill those rows with the average of the data in that row, and then I just take the classical MLE estimate, let's say for a Gaussian or something like that. Just start with something, okay? Use some common sense answer to initialize, and then we need to form the joint likelihood and compute the sufficient statistics, right? Compute the responsibilities, right? That's the sufficient statistics. So let's see how we're gonna compute the sufficient statistics. So so tell me what's going on here. So I fix the parameters, right? The parameters are fixed, okay? And I'm going to compute the sufficient statistics, right? These are posterior distributions. So given the data D that I have observed, okay? And I'm assuming basically the data come from a Gaussian. Here there's no Gaussian mix or anything like that, right? There's only one Gaussian that I'm assuming, but I am trying to basically account for the fact that the data xi, they're not complete data, they're missing data. So my likelihood is a Gaussian, so the log likelihood, there's no such a thing as joint log likelihood get, right? I put all the data here, known and unknown, okay? So I get the log of a Gaussian. But I need to take an expectation, and the expectation is going to be with respect to what? You remember in this step is the expected joint data log likelihood. Here, the expectation is going to be with respect to what? What are my hidden variables here? Say it again? The missing data. So we're going to have to take an expectation with respect to what distribution? I mean, extrapolate from what we did with Gaussian mixtures, right? So it would be, what is the posterior we're gonna look? Before we had the posterior of Z given X. Here it would be the posterior of the hidden variables given the visible variables. And how difficult would be to actually compute the posterior of the hidden variables given the visible variables. For a Gaussian, you can take the conditional distribution of anything with respect to anything analytically. Right? If you say, I know part of the variables, I don't know the rest, the conditional is written in the books. It's analytical. And I'm going to give it to you in a second. So the expectation here in the log likelihood, right, will be with respect to the posterior, right, that's why I put D there, of the hidden variables, okay? So if you expand the log, so for a multivariate Gaussian, I push, remember the parameters are constant, okay? The parameters are constant, so I am pushing the expectation, everywhere you see xi contains the visible variables, the data, and also things that I have not observed. Okay, so everywhere you see xi, I'm going to push the expectation in, and eventually you can write this expected log likelihood as minus n over 2 log of the determinant of sigma minus n d over 2 log of 2 pi. The Gaussian here is of dimension d, and then I have trace of sigma minus 1, and then I have the expectation of xi minus mu transpose. So I really need to compute the responsibilities here, the sufficient statistics, is the posterior expectation of xi and the posterior expectation of xi transpose. Okay, where again, xi, looking at each row, contains what I know and what I don't know. All right, so what we need to do is somehow we need to compute these responsibilities, these posterior probabilities, equal to expectations that we discussed before. And again, the key ingredient here is that if I put all my hidden variables in a vector form and all my visible variables like that, the distribution follows a Gaussian form, right, from the condition of a Gaussian. And here is basically the mean and the covariance. Everything is analytical, okay? The subscripts, basically H and V, tells you which columns in each row you are going to take, right? So this involves hidden visible variables, visible, etc., all the combinations. If you want to make actually life easy, what you can do is on the top of vector x put what you don't know or what you know, on the bottom put the rest, But the idea here is this is the posterior distribution that this expectation refers to. So if you try to take the expectation of xi contains the hidden variables and the visible variables, so I arranged them that way. These variables are fixed to whatever we were given. So here we will have to take the expectation of the hidden variables. And what is the expectation of the hidden variables? Mi. All right? Similarly, if you take the expectation of xi transpose and you expand, the visible variables remain as is, and you notice you get here the expectation of the expectation on even this pointer has died. So today you see even the pointers need a vacation. All right? Even the pointers need a vacation. All right. So here we have the expectation of the hidden variables, but here you notice it is the expectation of the hidden variables transpose, which actually immediately tells you that if by mistake you go everywhere and you substitute the x hidden variables with their expected value, the answer will be wrong, because you will be missing actually the expectation of xh transpose. Okay, so you'll be missing basically this term. So once you compute this, right, so what you need to do is put these things back on your functional, right, plug in all these values in here, and then take derivatives with respect to the parameters, and the parameters here, the Gaussian is the mean and the covariance. If you take derivatives, you actually, what you get is, you basically, obviously, it's a Gaussian. You get the MLE equations for the Gaussian, but notice again, when you compute the covariance, you don't get E of xi transpose. You get the expectation of xi transpose, and that expectation is given from the distribution that I gave you in the previous slide as mi transpose plus the covariance of that posterior. Okay? All right, so that's the covariance, so the expectation of xi transpose is given by this. Again, you cannot just substitute what you don't know with their expectations. That will not be consistent with the EM algorithm. Now, if you substitute by mistake, it is very possible, right? Because at the end of the day, you never find the global optimal, in this case, that you may get something reasonable. May happen, but it will not be right. Okay, it will not be right. So, so this is a very nice problem from Murphy's book. You have a 10-dimensional Gaussian. You're given data, 100 basically samples from this 10-dimensional Gaussian, but 50% of the values of the samples are missing, right? So we don't have 50% of the samples. The question is, can you actually go and make a reasonable estimate of the MLE things? And you can see here, it compares basically the true values versus the imputed values using the expectation maximization on one side and then the two parameters on the other side. So basically, actually, what you can do is, right, if you knew all the parameters of the Gaussian, then you know the distribution of the hidden variables given the visible variables. And if somebody tells you, can you now fill the gaps and tell me what the hidden variables are, the obvious thing to do is take the mean values. So this is exactly what is being plotted here. So if you knew the two parameters, right? You compare the imputed versus the true values. They're supposed to be on the diagonal, but you notice EM algorithm does extremely well, okay? And practically, actually, when you do this problem, you realize that the performance of EM in filling the gaps, basically in the metrics, is as good as if you knew actually the true values of the multivariate Gaussian. So that's very nice, and I think there is an example somewhere in Murphy's book where you can do this algorithm for images, and you can see when you have half of the image missing, you can use this version of the EM algorithm and figure out everything that is missing. So you can have fun because you can have one person disappear and then you recover him by accident or not. All right, 120. Okay, let me start this, right? So I mentioned that when you think of the EM algorithm, don't wait for somebody to give you a problem of a mixture and you say, oh, the EM algorithm. You have to use your mind and say, you know what? Maybe this looks like an EM algorithm. Maybe I can do some iteration similar to the EM algorithm. So without showing you any slides, can you actually think how the EM algorithm may be relevant to the student's t-distribution? So if you want to do an MLE estimate, given data that are sampled from a student t-distribution, why maybe an EM algorithm may be useful? If you get the idea, the rest is algebra. So how does the EM algorithm may be relevant to do MLE in the student t-distribution?
Degree of freedom in the sigma is not optimized. To find out that two parameters, we use the algorithm.
Yeah, no, but to do EM, right, I need to have something missing. So in a student t-distribution, what is missing? I mean, if there is no some latent variables, there is no EM algorithm. It's not just playing with the parameters, because like when we did the Gaussian imputation, data imputation problem, half of the data were missing. So if I tell you here data from student T, compute the parameters using the EM algorithm, what is missing? You know what? Can anybody hear you? Degrees of freedom. No, everything, you know, well, we need to compute the degree of freedom, right? It's part of the parameters. We need to compute that as well. So what is, you know, how can we make something to be missing? Like how can you say to me, can you disappear now earlier than normal so we can finish the class now? Same idea. How do you make something to be missing? So I'm going to put you the equation because time is short. And do you remember the definition of the student t-distribution? Remind me, what's the definition? I mean, this is from where the student t-distribution comes. We use this, I think. I know we used it last semester, and I think we used it early on in the course to literally define what the student t-distribution is. So how do we define, looking at this equation, the student t-distribution? The student t-distribution is what? Does it ring? So what does it, how does it ring? You know, we spent 2 lectures discussing about Gaussian mixtures, etc. Why is all of these things related with the student t-distribution? What is there that tells you, you know what, this is good? So what do I have here? I have a mixture of infinite Gaussian distributions of different basically variance, covariance, or different precision defined by this gamma distribution. All right? So effectively, our latent variables are literally Z, all right? Because the idea is, you know, what we have is really Gaussians, data coming from a Gaussian, but we're using a Gaussian mixture, and obviously we use an infinite Gaussian mixture, and we don't really know to which mixture components of the axis belongs. And it's not like because this is an infinite mixture that xi is going to belong to this component alone. It will be actually coming in the context of posterior probabilities, right? Which is just fine, okay? So actually, we can think of this as a mixture of Gaussians, infinite Gaussians with a Z. And if you think of that, all right, what you need to do is you need to form the joint log likelihood. The joint log likelihood means if you knew Z, and if you knew X given Z, the joint log likelihood will actually be the this log of this Gaussian, all right, and the log of the gamma distribution. You agree?
Yeah.
Okay? And summation over all the data points. I'm expanding the Gaussian, I'm expanding the gamma distribution, and I only have simplified things here by introducing this Mahalanobis distance to make things very simple. So basically, we have this joint log likelihood, and to apply the EM algorithm, really you need to do first, you need to compute the posterior responsibilities, right? The sufficient statistics, if you like. And once you do that, then you have to maximize with respect to the parameters. And the parameters in this problem are basically the sigma, the nu, etc. So it comes out, and I'm going to have to drop you here. It comes out that the optimization problem, the EM algorithm, works very nicely for estimating nu and sigma, but for the degrees of freedom that someone mentioned, unfortunately, you cannot actually get the closed form solution the way we have done up to now. Okay? So if you work out the algebra actually, and I advise you to do it because it's straightforward but involves a lot of interesting, nice things out of it. So it comes out, if I can find it, so it comes out that when you compute the gradient of the joint log likelihood with respect to the parameter nu, right? It's not like you can set it to 0 and solve for nu. The problem basically has to be solved with some ideas from constraint optimization. So you have to do some sort of optimization loop to solve this problem. And you can optimize it fully, or you can just make one update with a constraint optimizer and continue on in this way. But this leads to what is called generalized EM, right? Generalized EM means, in this context, that we don't have closed form solution and you need to do some sort of optimization to update the parameters new, okay? So please look at this problem because it has lots of very nice ideas, and it becomes even a more exciting problem if somebody throws you data that not only come from a student t distribution, so you're going to take all these latent variables unknown, but it comes from a mixture of student t distributions. So you're going to have two sets of latent variables. You're going to have the z variables, right? The z variables here that tell you to what component its data, to what component in the mixture it belongs. And then you're going to have these variables ui, which will tell you what scale that component comes from. And even in that extreme case, believe it or not, all the algebra, if you don't hesitate to do it, it comes in one slide. Okay? The algebra literally comes in one slide and you can get lots of insights. And the only problem is the update again on the degrees of freedom of the student t distributions has to be solved with an optimization step. And I think I have to stop there. And so no lecture tomorrow, and I will see you after the spring break.